Welcome to my YouTube channel where I discuss topics related to data science. In the previous presentation, the DBSCAN algorithm was introduced using the old faithful geyser dataset to illustrate its density-based approach to clustering. In this presentation, DBSCAN is applied to the principal component scores of the wine dataset that were used earlier for K-means and hierarchical cluster analysis. This allows the clustering results from all three algorithms to be compared on the same dataset, highlighting their similarities, differences, and the situations in which each method is most appropriate. Agenda. Before beginning, it is worth noting that the concepts, principles, and working mechanism of the DBSCAN algorithm were explained in the previous presentation. That video also introduced density-based clustering and demonstrated the algorithm using the old faithful geyser dataset. The link to that presentation is provided in the video description and again at the end of this presentation for viewers who would like a more detailed introduction. In this presentation, the focus is on applying DBSCAN to the principal component scores of the wine dataset using Python and the scikit-learn library. The implementation in Google Colab is demonstrated, followed by a comparison of the clustering results with those obtained earlier using K-means and agglomerative hierarchical clustering. Finally, the presentation concludes with a summary of the findings and a brief discussion of future directions in this machine learning series. The implementation of DBSCAN can be summarized in the following steps. First, the required Python libraries are imported, including NumPy, Pandas, Matplotlib, and the relevant models from the scikit-learn library. The principal component scores of the wine dataset obtained from the earlier PCA analysis are then imported from the CSV file. Next, a systemic search is performed to determine suitable values for two DBSCAN parameters, epsilon and mean points. Instead of selecting these values by trial and error, multiple parameter combinations are evaluated using a nested loop, and the Silhouette score is used to identify the combination that produces the best clustering solution. Once the optimal parameter values have been obtained, the DBSCAN model is fitted to the dataset using the Euclidean distance metric. Finally, the clustering results are displayed as a scatter plot, allowing the identified clusters and any detected outliers to be visualized. The overall implementation follows the workflow shown here. The analysis begins by importing the principal component scores of the wine dataset obtained from the earlier principal component analysis. Unlike the previous DBSCAN example using the old faithful dataset, no additional feature scaling is required because the principal component scores have already been standardized during the PCA procedure. A nested loop is then used to evaluate different combinations of epsilons and mean points in order to identify the optimal parameter values based on the Silhouette score. Using these optimal parameters, the DBSCAN model is fitted to the dataset. Finally, the clustering results are visualized as a scatter plot, allowing the detected clusters and any outliers to be examined. The code for implementing DBSCAN in Google Colab is shown. As before, the commonly used libraries are first imported. These include pandas and numpy for data handling together with matplotlib for visualization. The relevant modules from scikit-learn library for clustering and evaluation are imported later. The dataset used in this example consists of the first two principal component scores obtained from the earlier principal component analysis of the wine dataset. The CSV file named x underscore train underscore reduce is imported from the sample underscore data folder, and the first 5 rows are displayed to verify that the data have been loaded correctly. Unlike the previous DBSCAN example using the old faithful dataset, no additional feature scaling is required because the principal component scores have already been standardized during the PCA procedure. A scatter plot of the principal component scores is then displayed. Next, the DBSCAN class is imported from the cluster module, while the silhouette score function is imported from the matrix module of the scikit-learn library. As in the previous example, a range of epsilon and min point values is explored systematically using nested loops. Parameter combinations that produce only a single cluster are ignored and the silhouette score is calculated for the remaining solutions. The combination producing the highest silhouette score is retained. Once the optimal parameter values have been identified, the DBSCAN module is fitted using the Euclidean distance metric and cluster labels are assigned to each observation. The unique labels are then displayed to verify the clustering results. Finally, the clustering results are visualized. In this example, 3 clusters are identified together with any observations classified as noise. The continuation of the code from the previous code cell is shown. The Python code is implemented in Google Colab as shown next. Before running the code, the CSV file containing the data must first be uploaded from its folder to the Google Colab environment. Once the file has been uploaded, the code is executed and the DBSCAN algorithm is applied. The optimized results obtained for epsilon and min points are highlighted here together with the silhouette score. The principal component plot provides the reference distribution of the known wine classes. Both K-means and agglomerative hierarchical clustering recover the 3 main groups successfully. The arrows indicate the few observations whose cluster assignments differ from the known classes in the principal component plot. Overall, the two methods produce very similar clustering solutions. The DBSCAN result is now compared with the principal component plot. Similar to the previous methods, the three main groups are recovered, although a few observations indicated by the arrows are assigned to different clusters from their known classes. Unlike K-means and hierarchical clustering, however, DBSCAN also identifies several peripheral observations as noise or outliers, shown by the orange markers. Comparison of the three clustering methods shows that each is capable of recovering the overall structure of the wine dataset. K-means and agglomerative hierarchical clustering assign every observation to one of the three clusters, whereas DBSCAN additionally identify observations located in low-density regions as noise or outliers. The small differences observed between the methods occur mainly for samples located near cluster boundaries. These results illustrate that no single clustering algorithm is universally superior. Instead, the most appropriate method depends on the characteristics of the dataset and the objective of the analysis. This presentation concludes the comparison of three widely used clustering algorithms using the wine dataset, together with the earlier presentations on principal component analysis, K-means, and agglomerative hierarchical clustering. It provides an overview of several important unsupervised learning techniques available in Python. The next presentations will shift to supervised learning by introducing regression analysis, where the objective is to predict a continuous dependent variable such as house price from one or more explanatory variables. Later in the series, additional clustering methods, including spectral clustering and Gaussian mixture models, may also be explored to provide a broader understanding of unsupervised learning. Thank you for your time. Keep exploring, keep questioning, and keep turning data into knowledge. If you found this video helpful, please subscribe to stay updated with future videos. I would also love to hear your comments, suggestions, and ideas for future topics. Until next time, happy learning.